have your lecture notes. Still the same lecture, Kalman filter, but this part I'm going to derive. Hopefully today we'll finish deriving the entire Kalman filter. Hopefully, I'm not sure. Okay, let's have a quick recall. Although we haven't learned Kalman filter yet, I keep telling you there's few facts you should have in mind while you are learning or reviewing probability. The first one is Kalman filter does the same thing like a Lumberg observer. Okay, the input and output of Kalman filter. This is Y, this is U, and I want to have my state estimate. All right, you have to have your problem in mind, okay? And now instead of using Lumberg observer, the difference between these two are Kalman filter assumes a stochastic linear system model that we are going to discuss a little bit in more details later today. And that's the modeling assumption different. The second one is it's optimal, okay? It's optimal in certain sense. And a solution I already tell you, Kalman filter is just this. What is it? It's a conditional expectation. Kalman filter is nothing but a conditional expectation. Okay. Why is that? Today we're going to answer these two, then we derive the entire Kalman filter. First of all, why this guy is optimal? Why conditional expectation is optimal? In what sense it's optimal? And how do we derive those conditional expectation formulas based on the modeling assumption? That's what our goal is today. Okay, to understand this, you should have to understand the so-called minimum mean squared estimation, MMSE. Have any one of you heard about this or learned this before? Did you take machine learning class? Yes? Did you learn this?
Maybe
another name.
Not this name.
Okay. Did you learn Gaussian random vectors or random variables? Random vector, I think. Did you learn Gaussian random vectors in the machine learning class?
This is the first part of such a thing.
Oh, okay. Maybe many of you haven't taken machine learning class. That's another core course you have to take. Okay, let's direct jump to the minimum mean square estimation. All right, let's jump out of the box. Let's just think in general. We have a general problem. Suppose we want to estimate the value of a hidden random variable. What do I mean by hidden?
Cannot directly measure.
Exactly. So I cannot measure it. Okay? I can only guess its value from another observation that I can directly measure. So I want to estimate the value of this x based on relations, observations of a related vector y. Okay, that's roughly almost all estimation problem. Okay, let me repeat. So you can think of all of this estimation problem, even majority of machine learning problem is trying to solve this problem. Let's think you have the famous ImageNet. Okay, you have billions or millions of pictures and you want to tell whether it's dog or a cat. Okay, what are hidden variables you're trying to estimate? It's a label. So whether this guy is cat or dog. Okay, so it's x equal to 0 if it is a cat, x equal to 1 it is a dog, let's say, right? So you want to use your measurement y, which is all the pixels of all those images, to best estimate the value of x. The x is 0 means cat. X is 1 is dog. Did I repeat the same order or not? I forgot. So anyway, so that makes sense? You don't know, based on the observation, it doesn't tell you this hidden variable x, which is the label of this picture, but you can try to estimate it from images. So the entire neural network is trying to give you a so-called best classifier, right? So you're doing estimation in that case. Your face recognition, whether it's you or not. That's exactly estimation problem. So majority of the things you're dealing with in machine learning or in signal processing, all of them, most of them can be thought of as an estimation problem of something you want to use measurement from Y to estimate something hidden that you want to know. Okay, are you with me? Okay, so this is very generic, general class of problems. And I'm not sure whether how does this sound like, does this sound similar to the least square problem we described to you before? We want to estimate hidden variable theta from measurement, and we don't directly measure theta. So this is also an estimation problem, if you think. It's a least square problem, but it's just a deterministic estimation problem. All right, so now in this lecture, we are going to take a little bit jump. We don't think about them as a deterministic relation. So this is almost like, I think Y is a linear, is a matrix times theta. And this matrix is deterministic, right? We're having an almost deterministic relation between the hidden variable and the measurement. Now, for machine learning, or for a Kalman filter, for the things like this, we are going to take, I think, a much more powerful viewpoint, which is probabilistic relation. How these two are related. If you tell me the distribution, joint distribution, then we know exactly how they are related. So typically the relation between the hidden variable and the Y can be described by a probability. This is probability. This is the PDF, right? Probability density function, or PMF, right? Let's say Pij, if there's discrete values, that is PMF, probability mass function. If you tell me these two joint distribution, this is the joint distribution of these two random vectors or random variables, then I know exactly how they are related. At least this is the knowledge in our mind, how they're related. Okay. Now I'm going to define a so-called estimator. So estimator is this block. You tell me, you send me an input to the block, which is a measurement. I tell you my best guess. In the image recognition case, this will be a picture. This guy will be dog or cat. Okay? You write a function in Python, MATLAB, C++, whatever, and the function take input of image and output tell you, okay, this is my best guess, which is, I will tell you this is dog, maybe wrong, that's fine. Okay, I can, so for example, I can say a simpler example that I like temperature, okay? Because I love Shenzhen's temperature so much. So let's say Shenzhen temperature, let's say Y, and this Y typically will have a number. The small y is deterministic, okay? It's a number. I see a number today. I'm not sure whether today is 26 or not. Maybe colder than that, cooler than that, okay? Then the output could be maybe it's Guangzhou's temperature, right? But I can say this output is phi, a function of Y. Let's just say this is Y minus 0.5. I think, I'm not sure whether that's true, but Guangzhou is half degree cooler than Shenzhen. Okay, that's my knowledge. Okay, I can be wrong, but that's fine. This will give me an estimator of Guangzhou's temperature, x hat, in relation to Shenzhen temperature, which is what I can directly measure here. Okay, because for example, I can only measure my current location temperature here in SUSTech. Then I want to use that measurement to guess Suppose I don't have internet, okay? I can guess Guangzhou's temperature today, and my guess, the rule of this guess is y minus 0.5. Okay, in this case, my function will tell me, okay, it's 25.5. What I'm talking about is that estimator just maps the measurement from the just maps the measurement y to the hidden variable guess. You don't know exactly what the hidden variable is. You cannot directly measure them. You just guess them, right? This is a guess. It could be good, it could be bad, right? So maybe Yuntian will say By is 2 times y. That will be 52 degrees. You think that's ridiculous, it's wrong, right? But he can argue that he thinks today is, he knows something that we don't know, right? As I mentioned, probability is just something that about our own kind of belief about uncertainties, okay? So we have to have a rule or criteria to determine what estimate is good. Is this good? Or this one is, which one is good? Which one is better? Most of you think this one is better based on common sense, right? But common sense doesn't mean anything. Okay? So everyone believes something is like that. It doesn't mean it's right or wrong. We have to have a scientific way to determine what's right and what's bad. Okay? Yeah, common sense is just complete. You don't need to believe common sense. Okay? Once well before the common sense, everyone in this world believes the earth is flat. Everyone, right? That's common sense, but it's wrong. You don't have to believe that. Okay, so mean squared estimator is just trying to say, evaluate what estimator is good or bad based on a cost function. It's similar to our least square problem, right? In least square, let's say in least square, we have yi theta I. Sorry, no yi. So we have, let's directly work on this example. So let's say I have this x and y are jointly distributed with this. I can do samples, right? I do some example, I see some realizations. So this is x1, y1, x2, y2, dot, 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 right? So these are distributed. So how do I evaluate whether estimator is correct or not, or good or bad? It's just the weighted sum. The sum is the expectation, right? Expectation is nothing but the values this thing takes multiplied by the likelihood that value occurs. So that will be like, I will evaluate the first one, I minus xi squared times probability of xi and yi. If I write it more clean, is x equal to small xi, y equal to yi, okay? So x may take multiple values. X and y jointly distributed. They take multiple values. And each of them occur with this probability. And for each of these cases, you will have an error. A sum over this error will give you a so-called least squared error. But this is in the expectation sense, so it's called a mean squared error. Any questions? Does this, this is our cost criteria. Can you define your own cost criteria? Yes. You can say this is a cube. You can say this is, I like this fourth. I like exponential, I like a log. Either way is fine, but this is most people agree upon. And this is so-called minimum mean squared error. Let's work on an example. Oh, that's Yuntian, that's your estimator, okay? Let's see this estimator. Other example. Suppose I, x, y are jointly distributed according to this table. Do you understand this table now? So x1, x can be 2 or 3, y can be 1, 2, and each combination occurs with certain probability here described in the table. Okay, so now I'm going to ask you, what's the minimum, what's the mean squared error of this estimator defined like this? Is this a deterministic function? This function is nothing, but if you tell me why, I will just multiply by 2, right? It's a deterministic function. If you send me the same y, I will give you the same output. That means deterministic, okay? All right, so how do you compute this? Let's plug in to the definition. So this is phi of y minus x squared. I need to make sure on average this error is small, right? We have to be able to compute the average. What is it? How do you compute this? Expectation is nothing but the summation over all the possible cases, right? The weighted sum of the value it takes. So for each pair of x and y, let's say if x equal to, let's say x equal to 1, y equal to, y equal to 1, x equal to 2. Okay, that will be my phi of 1 minus phi of 1 minus 2. Is that right? Yes. And the square times the probability this case occurs. What's the probability? 0.4. Okay. And the other one is phi of y equal to 1 minus 3 squared times 0.1 plus phi of 2 minus, let's say 2 squared times 0.2 plus phi of 2 minus 3 squared times 0.3. On average, that will be the squared error for us. It's the mean squared error. Or we can compute this number, by the way, very easily. This guy, phi of 1 is 2. 2 minus 2 is 0. This is exactly, right? So your estimator in this case is perfect. But only perfect for one case doesn't mean anything, right? You have to make sure you cover the other cases. What about this? This is a 0.1. Yes, right? This guy is 0.8. 0.2 minus times 4, right? This guy is 0.3. Overall, I have 1.2. That's the mean squared error. Is this good? I don't know. Compared to what others? So then you should ask, okay, if this simply multiplied by 2 may not be the best, what would be the best? The best will be given by a function that minimizes this mean squared error, right? So I can tell you we have a almost analytical formula for the estimator. The best mean squared estimator, so it's the one that minimizes this mean squared error. It's given by the conditional expectation. Let me repeat. The best minimum or the minimum mean squared error estimator is given by the conditional expectation. Okay, so Yuntian, I will ask you. So how do you how do you explain this formula? What is this term? When capital Y is small y. Okay, yeah. Let me be more, okay. So when y is y, x given y equal to y, what does this symbol mean? This is when capital Y is small y, x is still random. Okay? When I know Shenzhen temperature is 26, Guangzhou's temperature is still random. And its distribution is given by another, it's distributed. Okay? I can compute this conditional density or conditional probability mass function. And then using this, I can compute the expectation of x given y equal to y, right? This will be a number, but that number depends on whatever you fit in for the conditions y. So if I give you 26, you tell me it's 25.5. If I give you 27, this guy will change as well. So this guy depends on the realization of the random variable y, okay? And the key property is that the minimum mean square error is nothing but conditional expectation, okay? Let's look at this case again. Let's see whether the conditional expectation will give us the best estimate, all right? So first of all, I know now by result in next slide, okay, by result in next slide, we know function of y, which is defined as conditional expectation of x given y equal to small y, is optimal. What optimal in the mean square sense, okay? So let's compute this. What is this? Let's check. Phi of y is expectation of x given y equal to small y, okay? I'm going to, the quiz will be about this as well, right? Today. How to compute this? Y is discrete, right? So y, I just enumerate the cases. Y can be 1, 2. Let's say if y is 1, then this is what? Expectation of x given y equal to 1 equals. So when y is 1, x is still random. Let's just repeat with me, okay? When x is y is 1, x is still random. It takes value 2 and 3. It takes value 2 with probability of what? 0.4 divided by the whole thing, right? So it's relative weight of this in the entire row. Okay, so this is 0.8 plus 3 times 0.2. Okay, so that will be 2.2. And if y is 2, then we get x given y equal to 2, which is when y is 2, x still random. It takes values 2 and 3 with probability 2 times 0.4 and 3 times 0.6, which is 2.6. Are we done? No, we only find a function. Is this a function? What is a function? Function is a mapping from argument to a value, right? So is this a function? Yes. You tell me a y, I can tell you what its value is. If y is 1, then tell you 2.2. If y is 2, I'll tell you the best estimate is 2.6. Let's see. So our best estimate, so minimum mean squared estimate, is a function of y. And this y is not, you don't have a formula, okay? Well, you do have a formula, you don't have a, it's not continuous. It's not like a 2x or something like that. It's divided by cases, right? So this is 2.2 if y is 1 and 2.6 if y is 2. Y can only take these two values, right? Now I can compute the minimum mean square error. So I would say expectation of this minimum mean square error of y minus x squared. We know how to compute this now, do we? But it take so how many cases? Sorry, these are now I need to plug in the capital Y, because I don't know what Y I'm going to see in reality, right? You can take with multiple values. So let's divide this case. Let me use another color. So in this case, when Y is 1, let's say, first of all, let's pick Y equal to 1. Y equal to 1, I always guess 2.2, right? So it will be 2.2 minus the cases for x, right? X equal to 2, then there's 2 squared times the probability of this pair occurs, 0.4, plus y equal to 1, I still guess 2.2 minus 3 squared times 0.1, plus, if I say now y equal to 2, then I always guess the estimate is 2.6 minus, first one is 2 squared times 0.2 plus 2.6 minus 3 squared times 0.3. This number would be, sum them together. If you believe me, I don't typically. I got 0.2. Okay, this is 0.2. Yuntian's estimator is 1.2. No, not his, okay, so let's say previous one, this guy is 1.2. This guy is 0.2. Can you make it smaller? If the theorem is correct, then it won't be. And I can tell you the theorem is correct. Okay? So this is the best you can hope for. So how to design the best estimator? Conditional expectation. If you know that, you know almost everything about estimation theory. Well, there's other ways. There's a Bayes filters, there's particle filters, there's Kalman filters, there's extended Kalman filters, ensemble Kalman filters, uncensored. So there's so many different things, right? All of them are based upon conditional density. Some of them take expectations, some just take the maximum likelihood. The key is to find conditional density or conditional distribution. Okay, I think we have enough, all right? So I wouldn't prove this, and I typed it. I typically prove them, right? It's pretty easy to prove. The steps are easy to follow, but it's conceptually hard. So every step, you may have question mark in your mind why we can do this. It seems 90% correct, but they just don't 100% get it. That's the way I think many of you will experience as you read through the proofs. And I think, but after we go over this again, as you review before the final exam, you check them again, your understanding will be different. Okay. Now, let me summarize. Now you finish almost the entire estimation theory, especially the part related to Kalman filter. So minimum mean squared estimate is just conditional expectation or conditional mean. That's the first one you should remember. Okay, I can ask you to repeat. The minimum mean square estimate is conditional expectation. As simple as this sentence, okay? And to continue, but the question is that, oh, well, did we solve everything yet? We have to be able to compute the conditional expectation, right? How do we compute? By definition again? The most general way is directly to compute the conditional mean is by definition, of course. Let's say by definition, well, we can know conditional density for sure. So expectation of y given capital Y equal to small y. We just need to compute this now, all right? If you think about estimation, all it boils down to is just the computation of conditional expectation. So by definition, this will be x, fx given y, and dx. Okay, I will say most estimation problem is trying to do this. Okay, that include particle filters, things like that, right? And but this is very hard to compute in high dimensional space, okay? In high dimension. Okay, when x and y are jointly distributed and there are 10 dimensions or 100 dimensions, multi-dimensional integral is really hard to compute, even numerically. So essentially, common filter is nothing but trying to find a clever way to compute this. You first need to understand what he's trying to prove or trying to compute. There's some part is conceptually the result, and some part is a technique, right? There's some tricks. So the essential part for common filter is just they're trying to find a smart way to compute this. Okay, let's take a break, and we will resume next.